to have this in a mechanical system? Okay, it's impossible. Why? Anyone? Yes. It won't come back, right? When you let go of the weight, it just gonna you know what I mean? It will not oscillate. Yeah, okay. So it just on its own. So it's impossible to have a what? Unspring system. Are we clear? Okay, this is impossible. I know it's obvious, but I don't like to. Okay, so if you have a system like this, okay, how do you draw the free body diagram? Okay, so let's say we are going to put a displacement y. So if we're going to have a displacement y is equal like 0.15 again, when t is equal to 0. Okay, so how does the free body diagram looks? Okay, so let's make things not complicated first. What does a spring want to do? Extend or contract? You want to grow longer or become shorter? The spring extension. Longer, yes or no? So what will happen if we have 0.15? You have to pull the spring what? Down. So I will call this our spring force. So this distance that we have just declared, this is our 0.15. Okay. Then if we look at the mass, right? And we know that we are going to pull it down by 0.15, right? The mass will have a reaction force, and the reaction force will be going upwards based on Newton's what? Third law. Right? Remember yesterday we did this example where we have a what? Where we have a reaction force from point B, remember? And then this is our member, remember? Right? This is our member, I can't remember, what was it? Let me check. Our member what? Our member BC, right? So if this is our BC, right? So we also draw a what? A reaction. Action equal reaction, same in magnitude, different in what? Direction. Are we clear? So this is how I want you to construct your what? Free body diagram. Okay, you have to be crystal clear on this. Okay. Let's look at a spring. In parallel configuration. Okay. So when we declare a spring in a parallel configuration, what it means is this, okay? So this is our system. You have one spring here, and you have another spring here. So we call this spring in a parallel system. So this is K1, okay? This is K2, and this is supporting our mass M. So in parallel, it's very similar to what you learn in electricity, okay, or electrical engineering, where you have resistors in parallel and resistors in what? Series, isn't it? Very similar. So the equivalent, okay, the equivalent stiffness, okay, K equivalent, is equal to K1 plus by what? K2. Okay. So if now we were to calculate the natural frequency, what we have is omega n will be equal to K equivalent over the mass. Okay, so therefore this is equal to K1 plus by K2 divided by M. Okay, and the units over here is radians per second. So now let's try to do example number 1. Okay, let's try to do example number 1. So for example number 1, I need you all to go on to Wednesday notes. Okay, and it is this. Okay, you have a system here. You have a mass at the center, and on the left-hand side, you have 2 springs. Okay, and on the right-hand side, you have also 2 springs. Okay, so you see this sort of configuration, and it highlights that the springs are originally what? Compressed. I repeat again, it highlights that the spring originally what? Is compressed. Okay, I'll give you 2 minutes, okay, to draw the free body diagram on your own now. Okay, no. I will draw the first free body diagram. Okay, I will draw the first free body diagram, and then later on you draw the second free body diagram. Okay, I'll do the first. It highlights the fact that the springs are under what? Compression. That is the rule. You have to obey that the springs are under compression. Physically, does it make sense? Is anyone struggling to see that the springs are in compression? Right, so these springs are originally longer, okay? And to squeeze something in, right, the spring has to be compressed so that M will be at the center, okay? So now we are going to sketch what does this mean? Freaking big multi-body free body diagram. Are we clear? Okay. Crazy, Mark. Right? So now I'm going to write down here the first one, the springs are in what? Are in compression. Okay. So we have one spring over here, another spring over here. They are in what? Compression. So let me change color. Okay, so you can see better. They are in compression. Okay. And then on the other side, the springs are also in what? Compression. Okay, you can see that. Okay, so you push it in, then the springs are in compression. Now on the center, we have a what? We have a load. Okay, now on the center, we have a load, a mass, sorry. We have a mass down here. Okay, we have a mass. So on this mass, right? So this is our mass. And these are our Ks. And we apply Newton which law? That law. Oh, sorry. Yeah, my wife say I got a type of disorder. Everything has to be that way or not, I go crazy. She's right. Agree or disagree? Okay, I give you 2 minutes now. Now, I want you to, are you struggling with this? No, right? Okay, now you're going to apply this free body diagram stuff reaction 2P, 3A, 2Q, whatever. Okay, you just apply the same what concept. Now, what will happen now? If now I'm or we are going to push this by a distance x. Draw the free body diagram for me. We are going to push it towards the what? Towards the right by x. Okay. Let's talk about this problem. On the left-hand side, what will happen to the spring? Will become longer. On the right-hand side, what will happen to the spring? So your free body diagram is controlled by your what? Whether your spring extend or contract. Use the same principle now, draw a free body diagram. And show me your order. Or see, did it change? 2 minutes. Talk among yourself, be quiet, talking like a bit good. No, I can't hear you. 30 more seconds to go. Who is very sure about the answer? Thumbs up. There's Dave. Sit down. Draw your answer and explain.
Okay. So because the box has moved to the right a little bit, that means the springs on the left are going to be extended, while the springs on the right are going to be compressed even more. That means that because of the equation for spring force, which is K over X, the force on the left is going to be even smaller, but in the same direction as when it was just being compressed on all sides. However, the spring on the right, because their displacement is even more now, the forces are going to be greater in magnitude, but still in the same direction. Where's Dr. Eugene?